Let us solve a problem related to the stator design of induction machines. Let us read out the question and denote the parameters given. Determine the main dimensions, number of radial ventilating ducts, number of stator slots and the number of turns per phase of a 3.7 kilowatt. That means output rating of that induction motor is 3.7 kilowatt. 400 volt, its voltage is 400 volt. 3 phase, 4 pole. There are 4 number of poles. 50 hertz, frequency is 50 hertz. And it is a squirrel cage induction motor and it has to be started by a star delta starter. This point is important. So, the motor is started by a star delta starter. So that means the delta side of the starter will be connected to the stator. So stator will be delta connected. That point is important. Stator is delta connected. Then work out the winding details. Assume average flux density in the air gap. So we know that is the B average is equal to 0.45 Weber per meter square. Ampere conductors per meter, that is AC, is equal to 23,000. Then efficiency is 0.85, power factor is 0.84. Machines rated at 3.7 kilowatt 4 pole are sold at a competitive price. So the design feature is a competitive price. That means it should be designed with a low cost. So therefore choose the main dimensions to give a cheap design. Design should be cheap. Price should be competitive. So we have to choose the L/T ratio corresponding to cheap design. So what will be the range of L/T ratio? It will be from 1.5 to 2. So we have already studied the value of L/T ratio corresponding to different design parameters, design features. So here the required design feature is a cheap design. A low cost machine has to be designed. So L/T ratio should be in the range 1.5 to 2. Now the winding factor and stacking factor are also given. Winding factor is 0.955. Stacking factor is 0.9. Okay. So even if the winding factor is not given, we can assume it as 0.955. If any other details for calculating the winding factor is not given, we can assume the value as 0.955. So now let us solve the problem. So now let us move on to the solution of the problem. So we have already said that while starting with the problem of designing of an induction motor, when we are using the output equation Q is equal to C0 D square L into Ns, Q should be the input power expressed in kVA, input kVA. So what we have is the output power in kilowatt. So we have to convert output power in kilowatt to input kVA. So input kVA rating Q will be equal to output kilowatt rating divided by efficiency into power factor. This is the first step in solving the design problems of induction machines, induction motors. Always convert the output kilowatt rating into input kVA rating. So output kilowatt is 3.7 divided by 0.85. Efficiency is 0.85 and power factor is 0.84. And on solving this, you will get the value of input kVA as 5.18 kVA. So now we have to find out the main dimensions. In the question, it is being asked to calculate the main dimensions. That is, we have to calculate D and L. So we are always calculating the main dimensions D and L using the output equation. So this is our output equation. Here we know the value of Q, we can calculate C0, and we know the value of Ns. Then from here we will get the value of D square L. So we know that D square L is equal to Q divided by C0 into Ns. So our Q is 5.18 divided by, what is the equation for C0? 11 into B average into AC into KW into 10 raised to minus 3 into Ns, small ns. So Ns is the synchronous speed in RPS, which is not given. So how will you calculate Ns? Equation for Ns, synchronous speed in RPS, is 2F divided by P. That is 2 into frequency is 50 divided by number of poles 4. It becomes 25 RPS. And then we can write D square L as 5.18 divided by 11 into B average is 0.45, AC is 23,000 into KW is 0.955 into 10 raised to minus 3 into 25. So answer will be 1.91 into 10 raised to minus 3. Unit is meter cube. Unit of D square L is meter cube. Because D and L are in meters, so meter square into meter. Unit is meter cube. So this is D square L. Now we have to separate D and L from this product D square L. And we have also discussed this question. How to separate D and L from D square L? It is based on the required design feature or based on the peripheral speed. So here in this question already the design feature is given and it is cheap design. The required design feature is a cheap design, and we already know the value of L/τ ratio corresponding to cheap design. That is, it can be from 1.5 to 2. So you can take any value in between 1.5 and 2. You can take 1.5, you can take 2, 1.75, 1.6, any value you can assume. So for instance, let us assume L/τ is equal to 1.5. Okay. So L/τ is equal to 1.5 means L is equal to 1.5 τ. What is τ? τ is pi d by P. So 1.5 into τ means pi d by P. So we got L is equal to 1.5 into pi into D divided by P. Number of poles is 4. So on simplifying this equation, we will get a relationship between L and D. So multiply 1.5 into pi and divide it by 4. Then we will get so we will get L is equal to 1.178 D. 1.5 into pi divided by 4 will become 1.178. So L is equal to 1.178 into D. Now substitute this value of L in terms of D in D square L. Okay. So we have D square L is equal to 1.91 into 10 raised to minus 3. Okay, D square L is equal to 1.91 into 10 raised to minus 3, and we got L as 1.178 D. So it will become D square into L is 1.178 D, which is equal to 1.91 into 10 raised to minus 3. D square into D cube. 1.178 D cube is equal to 1.91 into 10 raised to minus 3. Now simplify this equation and find out the value of D. So D will be 0.117 meter. This will be the answer you are going to obtain. So now substitute D in this equation. So substitute the value of D here. Then we will get L as 0.13 meter. This is just an approximate value. It will vary from 0.13. It may be sometimes 0.129, 0.12 something also. Okay. So these are the approximate values of main dimensions D and L. So now we have to design the winding. So for designing the winding, we have to calculate the turns per phase. Then we have to calculate the number of status loads, etc. Okay. So before that, one more thing is being asked in the question. So you have to calculate the main dimensions. See the question. Determine the main dimensions, number of radial ventilating ducts. Okay. So number of radial ventilating ducts will depend on the length of the stator. So in module 1 also we have studied about the provision of radial ventilating ducts. So when radial ventilating ducts are provided in a machine, when the core length exceeds 0.1 meter, when the core length is more than 0.1 meter, we have to provide one radial ventilating duct. So here the core length is 0.13 meter. So we have to provide one radial ventilating duct, and the width of the radial ventilating duct to be used is 10 mm. So these are basic things that we have studied in module 1. So here number of radial ducts equals 1. Width of radial ventilating duct WD is equal to 10 mm. Now using this we can calculate the net iron length. Net iron length. So this is actually the gross iron length, total length of the core including the radial ventilating ducts and the insulation between the laminations. So net iron length will give us the length of iron portion only, and it will be equal to stacking factor into gross core length minus number of ventilating ducts into number of radial ventilating ducts into width of each duct, which is equal to stacking factor is given as 0.9 into gross core length is 0.13 minus there is a single duct of 10 mm wide. So 10 into 10 raised to minus 3. Okay. So the answer will be 0.108 meter. This is the actual length of iron in the core. So core design is complete with this. Main dimensions D and L are complete with this. Now we have to find out the turns per phase. We have to design the stator. So for the stator we have to find out the number of stator turns per phase. So we know that the equation, we have derived the equation for finding out the stator turns using the equation of induced EMF. So induced EMF per phase in the stator, per phase EMF is equal to, that is ES is equal to 4.44 F phi into TS into kW. So turns per phase TS is equal to ES, EMF per phase divided by 4.44 into F into phi into kW. So that means we need to know the value of phi. Value of phi is not given. So we have to calculate phi. So how will you calculate phi? Do we know the value of any parameter which is related to the flux? Yes, the value of B average is given, and we know that B average is equal to P phi divided by pi d L. It is given as 0.45. We know the value of number of poles, and we have already calculated D and L. So substitute these values and find out the value of flux phi. and you will get the value of phi as 5.5 into 10 raised to minus 3 Weber. 5.5 into 10 raised to minus 3 Weber. Substitute phi here and calculate the value of Ts. So Ts will be Es. Es is the EMF per phase. Here we have already noted down in the beginning that stator is delta connected. As we are using a star delta starter, the stator will be delta connected. So line voltage and phase voltages are equal, and the voltage is given as 400 divided by 4.44 into frequency is 50 Hz into flux is 5.5 into 10 raised to minus 3 into kW, the winding factor is 0.955. So on solving this, we will get the value of number of turns per phase Ts as 343. Okay, now we have to calculate the number of stator slots. Number of stator slots has to be calculated next. And we actually calculate the number of stator slots from the range of slot pitch, same as in the case of DC machines. But here the machine is having a rating 3.7 kilowatt. So it is a small machine, and we know that for small machines the slot pitch YSS can be less than 15 mm. Okay, the slot pitch can be less than 15 mm, but it should not be less than 10 mm. So it should be some value between 10 mm and 15 mm. So here we does not know the correct range of slot pitch. For small machines it is less than 15 mm. That is the actual thing that we know. So it should not be less than 10 mm due to some mechanical considerations. So what we actually do in this problem is that we will assume a value for slots per pole per phase. So while discussing about the theory portions related to the design of stator slots, we have said that the stator slots per pole per phase should be at least 2. Should be at least 2. Okay. So let us substitute a value. It can be an integer like 2, 3, 4, etc. and it should not be less than 2. So for instance, let us assume the slots per pole per phase as 3. 2 is the minimum value. We are assuming Q as 3. Okay. So it is the slots per pole per phase. So then total number of slots will be equal to number of phases into number of pole. That is 3 into number of phases 3 into number of poles 4. So 3 into 3 9, 9 into 4 36. 36 will be the total number of slots. So let us check the slot pitch. So with 36 number of slots, let us see whether the slot pitch value satisfies the required ranges. Okay, with the 36 slot, the slot pitch YSS is pi into D divided by number of slots, that is pi into, we have got the value of D as 0.117 divided by 36. So it will be some value near to 10.47 mm. It is almost around 10.47 mm. So it is less than 15 mm and more than 10 mm. So this value is acceptable. Okay. So we can accept the total number of stator slots SS is equal to 36. Okay, it is acceptable. So we have said that the minimum value should be 2. So what happens if we have chosen the Q as 2? What will happen? If Q is 2, we will get the total number of stator slots as 2 into phases into poles, that is 24. So if we find out the slot pitch with 24 slots, it will be more than 15 mm. Okay, if we proceed with a number of slots 24 and calculate the slot pitch, it will be somewhat a value 15 point something. That is, it will be more than 15 mm. That is not acceptable. So that is why we are taking Q as 3. So while you are solving problems, you can start with Q is equal to 2. It is a minimum value. Then you can check whether it satisfies the specified range of slot pitch. If it does not satisfy, then you can go for Q is equal to 3 and check whether it is satisfied. If it is okay, you can accept Q is equal to 3. So here this is a question from our textbook and they have already gone for Q is equal to 3. So the reason for taking Q is equal to 3 is that when Q is taken as 3, the total number of slots required, slots that we obtain, satisfies the slot pitch range. So we can take Q is equal to 3, then total number of slots become 36. Okay. So we have got the number of turns per phase as well as the total number of slots. Now we can calculate the total number of conductors. Total number of stator conductors is equal to number of turns per phase. TS is given. So in a single phase there are TS number of turns. So we have 3 such phases. So total turns is 3 into TS, and there are 2 conductors in a single turn. So into 2, or total number of conductors is equal to 6 TS, which becomes 6 into 343, which is equal to 2058. This is the total number of conductors. Okay. So after finding out the total number of conductors, we have to find out the conductors per slot. How many conductors are to be placed in a single slot, which is denoted as ZSS, conductors per stator slot. So that is total number of stator conductors divided by total number of slots, and it will be 57. Okay. So that means total number of, it is not 57, we can approximate the value that we obtain as 57. Okay, we will get some fractional values, but we cannot use a fractional value for conductors per slot. Okay, we cannot use a fraction because number of conductors per slot, how many conductors are to be placed in a single slot, it should be an integer value. So we have to approximate it to the nearest integer, and using this approximated value we have to recalculate the total number of conductors required. Okay, so actually by using this total number of conductors 2058, we will be getting some fractional value. We are approximating it to an integer value. Then by using this integer value, recalculate the total number of conductors required. So actual number of conductors is equal to 57 into 36. Actual number of conductors is equal to 57 into 36. Then actual turns per phase. Actual turns per phase is total number of conductors divided by total number of conductors is 6 TS. So turns per phase is total conductors divided by 6. 57 into 36 divided by 6, and that will be 342. So we have initially got it as 343, but in order to have an integer number of conductors per slot, we have rearranged the values And so for that, actual turns per phase becomes 342. Okay. So this is how we can design this induction machine.